Okay, section 4, on to the good stuff. Eigenvectors and eigenvalues. So what are they? First definitions, right? An eigenvector of an n by n matrix is a non-zero vector x, such that ax is equal to, this is the Greek letter lambda, ax equals lambda x for some scalar lambda. And lambda is the eigenvalue. Okay, so x is the eigenvector, and lambda is the eigenvalue, right? Basically, it says if you multiply a matrix A by a vector, and that's a multiple of the vector itself, that's that eigenvalue-eigenvector relationship. The multiple is lambda, is the eigenvalue. So although an eigenvector can not be zero, an eigenvalue can. You can have zero as an eigenvalue, and we'll see why in a second. Notice if I rearrange this, right, lambda is an eigenvalue if a minus lambda I times x is 0 has a non-trivial solution. As a non-trivial solution. And then the set of all these solutions are called the eigenspace. Okay. So let's take a look at this example. So we have a little 2x2 action here. A is given, lambda is 4, so I'm telling you that lambda is 4 here. Let's find a basis for the eigenspace corresponding to lambda equal 4. So we take a look at A minus 4i, right? And we get this matrix here. And I guess you don't have to augment because it's with zeros, but if you want to, go ahead. But this is the augmented matrix, obviously, with the column of zeros at the end. That's equivalent to this, so we do have our free variable, right? x1 is equal to 3/2 x2. x2 is free. There's only one pivot position here. So a basis for the eigenspace is 3/2 1, right? Because x2 is free, and x1 is 3/2 x2. So that represents a basis for the eigenspace. The eigenvalues of a triangular matrix are the entries on its main diagonal. This is very useful. And why do you think that is? Well, let's just take a look at the easy 2x2 case and see what's going on, right? So if you take a look at A minus lambda I, so this is triangular here, just generic. I just have A11, A12, A22 entries. Doesn't matter what the numbers are. And we look at A minus lambda I, we get this situation here, right? Now remember, we're looking for free variables. So right, it's an eigenvalue if this equation is 0 and it's got a non-trivial solution. In other words, they're free variables. And so free variables are when the entries on the diagonal is 0. So clearly if A11 is lambda or A22 is lambda, that's going to give you the 0. Okay, so that's very nice when you have triangular because it's easy to see what the eigenvalues are. If V1 and V2 up to Vr are eigenvectors corresponding to distinct eigenvalues, lambda 1 up to lambda r of a matrix A n by n, then V1, V2 up to Vr are linearly independent. Okay, this is important to know. In other words, eigenvectors from corresponding to different eigenvalues are linearly independent. So here we're just, I haven't really shown you how to find them yet. We're just kind of talking about them. So is it an eigenvector, right? Well, it's an eigenvector if you multiply A by 1 minus 2, 1 and get a multiple of 1 minus 2, 1, right? And if so, that would be that constant or that multiple is the eigenvalue. So that's how we're going to check that. And then this is similar to the one we did before, and this is similar to the one we just did in the notes. Okay? I think it's pretty similar for the homework. Okay?